Okay, today we're gonna continue. Can you guys hear me?
Yes.
Yes. Okay, thank you. Today we're gonna continue learning on chapter 9. Like I told some of you yesterday, when you study, please use my note as a guideline. Last time we talked about the classification of chemical reactions, including an old way of classifying chemical reactions based on the fashion of how the reaction works. What is the fashion of the reaction? We call those reaction combination, decomposition, single displacement, double displacement, and oxidation. And another way, which is a lot more commonly used, is classifying reaction into redox reaction and non-redox reaction. And in order to study redox and non-redox, we learned a bookkeeping system called oxidation numbers. And based on the oxidation numbers, we can tell whether a reaction is redox or not. And if it is a redox reaction, we can study which one or which substance undergoes the reduction, and which substance undergoes the oxidation. So we have a lot of terminologies in redox reaction as well. So when I review these, I don't know how many of you can recall the slides, can recall the notes. So this is how you study. You can kind of like put those images in your mind and when you study the whole chapter. Okay, today in the second half of chapter 9, we're going to study some details of chemical reaction, why there's a chemical reaction, and what are some terms, what are the factors affecting the rate of a chemical reaction. And the last part of it, we're going to study a term called chemical equilibrium. Okay, you have heard the word equilibrium before, but now we're talking about chemical equilibrium. Now, like I said earlier, this chapter is kind of like a few chapters wrapped together into a big chapter in Chem 101 because it's a fundamental. So sometimes those concepts are actually thrown directly at you, such as this one we call collision theory and chemical reactions. Basically, this page summarized a few statements that give you an idea of why there is a reaction. When a reaction happens, what conditions must be satisfied? Again, this is kind of like theory directly through to you because again, it's like a wrap up of all the individual chapters. We didn't learn much of the background, but should be fine. Like I said, they integrated pretty well for these statements. So here, let's take a look. In order for a reaction to take a place, what conditions must be satisfied and why there is a chemical reaction? First, no matter there's a reaction or not, reactant molecules, ions, or atoms, these particles are always moving. We know they possess kinetic energy. They're always moving around. Because they're moving, so they will bump into each other. We call that collision. So no matter there's a reaction or not, they're colliding with each other all the time, the reactants. Okay, so the first fact about reaction is particles collide with each other, reactant collisions. Now, in order for a reaction to happen, the collision must overcome a minimal energy, like a hill. You have to go over the hill in order for the reaction to happen. If the collision does not supply that enough energy, then the reaction will not happen. They will bump away. In order for them to bump and have a chemical reaction, that collision must have sufficient energy to overcome a barrier. That barrier is called the activation energy. Again, what is activation energy? Activation energy is a barrier. The molecules collide. If they don't have enough energy to overcome the barrier, we call that collision inefficient or ineffective. I mean, they're bumping away. But if they have enough energy to overcome the barrier, then there's a possibility of a reaction. And that barrier is called an activation energy, like this barrier. In order for go across the hill, you have to go across that barrier. Number 3, even though you have enough or sufficient energy to overcome the barrier, it doesn't mean you will necessarily have a chemical reaction. A third condition is the collision must be correctly orientated. So basically, when they collide, if the collision must be head-to-head, then there must be head-to-head collision. If they collide head-to-toe, then even though they have enough energy, the reaction may not happen. So collision orientation is also necessary in order for a reaction to happen. And these three statements summarize why there's a chemical reaction and what condition in order to be satisfied in order for a reaction to happen. And here, this picture shows you what the orientation means. You can see that when these two molecules collide like this, between the O and the C, all right, there's a reaction. But if they collide between O and O or N and O or N and C, no reaction, because the reaction happened between the collision of O and C. So that this picture kind of shows you, in order for a reaction to happen, these two molecules, the collision orientation must be correct before a reaction to happen, even though you have sufficient energy. Does it make sense, guys?
Yes.
Okay, again, these three statements you have to understand and be able to tell it out using your own language. Again, you don't need to memorize word by word. First statement, what is it? Molecules are colliding with each other all the time. But in order for a reaction to happen, the collision must to have sufficient energy to overcome a barrier, or we call that barrier the activation energy. If you have sufficient energy to overcome the barrier, the reaction is possible, but not necessary. In order to satisfy a reaction, the collision must have correct orientation. Means the atoms must be correctly oriented, colliding with each other for a reaction to happen. So again, you need to tell the story out and understand these three statements about a chemical reaction. Now, after you understand these three, let's take a look at these four factors that affect reaction rate. Again, you have to understand these three statements before we can explain these four factors affecting reaction rate. First, let's talk about this word rate. What does rate mean? Rate means speed. Basically means how fast or how slow the reaction is. Higher rate, reaction is faster. Lower rate, reaction is slower. Rate is nothing fancy but speed. So we're talking about these four factors. How do they affect the speed of a reaction? You have to memorize these four factors. The first one is the physical nature of the reactants. Second one is the concentration of the reactants. Third one is the temperature. Last one is if there's a catalyst is present or not. Again, four factors you have to memorize, not word by word, but you have to know these are the four factors: physical nature, concentration, temperature, and catalyst. So let's take a look one at a time. Why and what does it mean nature? What does it mean concentration? How do they affect reaction rate? Again, we're learning these based on the three statements. Hope you can still remember the collision statements. Okay, first let's take a look at physical nature. Physical nature mostly means the physical state of the reactant and the size of the particles. When reactants are in the same physical states, reaction rate is generally faster between liquid state than solid state. So if the reaction are liquid, the reaction is faster than reaction are solid. Reaction rate is the fastest when reactants are gas. Why is that? Because when reactants are gas, the particles are easier to collide with each other than with liquid, than with solid. Think about it, if you have solids, the contact area is very small because solids, I mean, there's like a compact state. So reaction rate is fastest when the reactants are gas, then faster than liquid and solids. and liquid state reactions are faster than solid state reactions. Why? Because the chance of collision. Gas collision is the most frequent, the biggest chance. Why? Because gas particles can mingle with each other very well. Now, if the reactions are solids, we know the slow reaction because solid is the slowest. The reaction rate will increase as the subdivision of the solid increases. As the subdivision of the solid increases. Again, we're talking about solids. Even though it's slow, it's still the reaction is possible, but it's slow. But we can still increase the reaction by increasing the subdivision. What does it mean? If you place two rocks contact area is only surface. But if I chop the rocks into sand, mix them together, you can think about which one collision is bigger, which one collision is more frequent. And this picture shows you, hey, you can see this guy actually blow some powders, and the flame is crazy. Why? Because the powders are fine solid particles, and when they're fine solid particles, they got a greater contact area, and the combustion is more violent. Okay, don't do this at home. I don't even know what that is. Called a lycopodium spores over a candle. I mean, I don't know that, but it shows you if it is a solid, if you increase the substitution, making finer particles, the reaction can also be increased. Again, all because of what? Chances of collision. Does it make sense, guys? First factor. See, we're talking about these factors based on what? While we learn about the reaction, about the collision. Does it make sense, guys?
Yes.
Okay. Second is the concentration of the reactants. Okay, concentration of the reactants. Higher concentration, faster the reaction. Why? Because in the unit area, you have more reactant present. High concentration means what? The percentage of the reactant is higher in a unit area. This experiment shows you. If you burn a wood stick in the air, the concentration of oxygen, we know burning is because of oxygen. The concentration of oxygen is like 20%. That's the percent of oxygen in the air. But if you burn it in pure oxygen, take a look what happens. The flame is much brighter. You will see purple, very beautiful flame. Why? Because pure oxygen, the concentration is much higher than the oxygen in the air. That is why. And actually, you guys, this week's lab, the property of gas, you will do this. You collect oxygen gas, I think, right, guys? You place a almost off wood splint into the oxygen. You will see that wood splint rekindles, okay, relight off, or the flame gets brighter. Why? Because the concentration of oxygen is pure now. In this bottle, the oxygen is pure oxygen. They collect some oxygen in the bottle. But again, if you burn it in the air, the concentration of oxygen is only 20%. The air we breathe, only 20% of oxygen. But if you burn it in pure oxygen, you see what happens. Okay, and that's why you have heard somebody carry a oxygen supplying, like breathe. They have a sign called no smoking. Oxygen doesn't burn actually, but oxygen facilitates burning because it's pure oxygen in those patients. Even a tiny sparkle will be big flame. Okay, we produce a big flame. Again, concentration means what? More reactants. Why? Because collision is more, because you have more reactants. Okay, that's number 2 factor. Anybody can tell me what's the third factor? The first factor is nature, physical nature. Second factor is the concentration. Third factor is what?
Temperature.
Temperature, very good. Okay, reaction temperature. Higher temperature, reaction rate is higher. Okay, that's the conclusion. Higher temperature, reaction is higher. Why? Because we know molecules, particles possess kinetic energy. When temperature is higher, speed is faster. Then the kinetic energy is higher. Kinetic energy means higher. It means what? The molecules are moving faster. Molecule moving faster means what? More collision. More collision, more reaction. So higher temperature, higher reaction rate. Now this scheme shows you the effect of temperature, what truly is the effect of temperature affecting reaction rate. As you can see here, when temperature increases, this curve shifts to the right, meaning there are more molecules possess higher kinetic energy. What does it mean? It means if we have a bottle of molecule, for example, or group of molecules, not everyone have the same kinetic energy. Somebody has a lower kinetic energy, somebody has higher kinetic energy, but most of the molecule has this kinetic energy. That's called a distribution. Okay, distribution. I don't know how many of you guys learn math or calculus. This is called distribution, just like we're a group of students or group of people. Some students perform the best, some students perform relatively poor. Most of the students perform this range. So it's called that distribution. The same for molecules. Some molecules are very excited, very high speed. Some molecules are slowed down, but most of the molecules is here. But if you increase temperature, you can see that the distribution chart shifts to the right. It means what? Most the molecules will have more molecules will have higher kinetic energy because of higher temperature. Again, higher kinetic energy means what? Means reaction rate is higher. Why? Because more collisions. Speed is faster now. And by the way, most of my class, I don't see a distribution, unfortunately. Somebody, I recall somebody asked me to grade on distribution. I don't do that in most of my class. I've never seen my class on distribution, which is, I mean, sometimes makes sense. Sometimes if we have a big group, there may be a pattern, but not all the time. But most times, if you have a big group of numbers, we will fall into this distribution. Okay, molecules fall into distribution for kinetic energy. And finally is catalyst. Okay, catalyst. First, what is a catalyst? Catalyst is something that increase the rate of a chemical reaction, but it will not be consumed. Okay, not be consumed. Two facts about catalyst. Catalyst is something that increase the reaction rate, but it will not be consumed. That means it will be regenerated. So you don't need a lot of catalyst, tiny amount. How many of you have done the lab of gas?
I've done the lab. I just need to answer the rest of the questions.
All right. What do you, anybody remember? What do you need to add to hydrogen peroxide to generate oxygen? What do you need to add to the test tube? Anybody? Did you add anything to the test tube in order for the hydrogen peroxide to generate oxygen? Anybody remember?
I think it was manganese.
Manganese oxide. That is a catalyst in that reaction. Okay, without it, hydrogen peroxide can still generate oxygen, very slow. You open a bottle of hydrogen peroxide, you can buy it from CVS. You will see bubbles, but very tiny, only a few. Why? Because the reaction decomposition of hydrogen peroxide is slow. But if you add manganese oxide, the reaction is much faster. You see that. Some of you haven't done the lab, go ahead and do it. You will see that the reaction is faster. That manganese oxide is a catalyst for the reaction. Catalyst means what? Reaction is faster. Hey, this lab is perfect for this chapter. I didn't realize that. Like I said, this is the first time one-on-one taught online, but it works perfect for this chapter. And also some other catalysts you can use for hydrogen peroxide. Some of you got a cut on your hand. You pour hydrogen peroxide on the cut. The blood has an enzyme that also can catalyze the reaction. That's why on the cut, you will see a lot of bubbles. That bubble is oxygen. That's why we use that to sanitize, okay, for antiseptic purposes. Okay, and so our blood has a lot of catalyst that can decompose hydrogen peroxide, by the way. Again, catalyst is something can increase the reaction rate, but without being consumed. Itself, it will not be consumed. That's why we don't need a lot, only a tiny amount of catalyst, because it can be regenerated. What catalyst does is it provides a alternate reaction pathway that have a lower activation energy. Remember what is activation energy? Activation energy is the barrier. If the barrier is lower, it means what? More guys can overcome it. More molecules can overcome, means more collision will be efficient. Again, activation energy is the barrier. If the activation energy is now lower, more reaction will take place because more collision can overcome that barrier. That's what catalyst does. That is the 4 factors affecting reaction rate. Does it make sense, guys?
Yes.
Okay, please understand those 3 statements. Okay, it's 3 statements about a reaction. And those 3 statements will help you to understand these 4 factors affecting reaction rate. Again, you don't have to memorize word by word. You need to know everything and be able to explain your own word. Okay, your final exam is multiple choice, so at least you can, based on the multiple choice, can provide the correct answer. Understand these topics. Okay, next, only one slide is about the thermodynamics of a reaction. Basically means whether the reaction in the end release energy or absorb energy. If the reaction in the end release energy, gives off energy, we call that reaction exothermic. Okay, exothermic. If the reaction in the end absorbs energy, takes in, we call those reactions endothermic reactions. And these 2 charts tells you why some reaction is endo, some reaction is exo. Take a look at the exo. The reason it is exothermic is because the energy of the product is lower. You are changing from a higher reactants to the lower product. So energy what? Drops. When energy drops, it doesn't go anywhere. It goes releasing. Again, the reason some of the reaction is exothermic is because the energy of the product is lower. You can see that this is the energy of the reactants. This is the energy of the product. Let me use a different color. Okay, this is the energy of the reactants. That's the energy of the product. You can see product is lower. It means what? Some energy is given away. That's why it's lower. Just like a bank account. If your bank account in the end is lower, means what? You spend money. Energy, money goes out. The same idea. Energy goes out means product energy is lower. That's why we call the reaction exothermic. Again, the reason is exothermic is because the energy of the product is lower. And by the way, you can see here, the barrier here is what? Activation energy. Okay, the barrier is the activation energy. Now, for endothermic reaction, it's now easy to understand. The reason is endothermic because the energy of the product is higher. Higher means what? You put money in. If your bank account in the end, your balance is higher, means what? You put money, you deposit your money. The same. Why energy is higher? Because energy absorbed. You take energy in. That's why your final energy is higher. Your product energy is higher. And we call that energy endothermic. Does it make sense, guys?
Yes.
Perfect. Last part of this chapter. Chemical equilibrium. Okay, chemical equilibrium. You guys have heard of this equilibrium many times. At least this is the 3rd time. The first time is when we talk about evaporation. Don't know how many guys you remember that purple flask I talk about many times. Evaporation means what? Means eventually the rate of evaporation will equal to the rate of condensation. Back and forth, they will be the same. The liquid level will not drop. Again, we're talking about sealed container. If it's not sealed, that means things keep going out. I mean, the bottle will be empty. But if you have a sealed bottle, then the liquid level will never drop at a certain amount after a certain amount of time. And that point, evaporation equals to condensation. Back and forth is the same. We call that what? Physical equilibrium. Why physical? Because evaporation is a physical change. Same idea. When we have a chemical equilibrium, means back and forth rates are the same. What rate? Reaction rate. because we're talking about chemical equilibrium. So if I have a reaction like this, hydrogen react with iodine to produce hydrogen iodide. This reaction is reversible. Means the reactants can produce the product hydrogen iodide, and at the same time hydrogen iodide can go back to the reactants, decompose. You can see that forward is a composition, combination, backwards is decomposition, by the way. But the reaction is reversible. That's why I use a double arrow. You can see double-sided arrow, means you can put back and forth. Now, at a certain time point, the reaction rate will be the same, back and forth. At that point, we call it chemical equilibrium. Why that happen? Think about it. If I initially only have these two guys, if I initially only have H and H2 and I2, the reaction is keeping going forward because I don't even have an HI, nobody come back. So if these two going forward, the concentration of these two will decrease, right? Because they're going forward, they're converting to the product because these two are converting to the product. So the concentration of these two will decrease. This is what happened here. Take a look. Decrease. See the chart? There's two decrease. Now, if the concentration decrease, guys, take a look at the back one we talk about. The reaction rate is related to concentration. If the concentration decrease, what happened? The forward reaction rate decrease. This is what happened here again. The decrease means the forward reaction rate decrease. Now, meanwhile, you get more and more of HI because they're producing more and more. More and more HI means the backward reaction will start to increase. Initially, it's zero. Why? Because initially you don't have any HI. One thing decrease, another thing increase. At a certain time point, these two will become what? Equal. When they're equal means what? No matter how many molecules go forward, how many molecules will be going back and decompose. Reverse and forward the reaction rate now equal. And that time point, we call the reaction reached equilibrium. Does it make sense, guys?
Yes.
Okay, again, initially I only have H2 and I2. The forward reaction is fastest because that's all we have. But when they start to produce something on the right, they would going to drop. When they drop, the forward reaction drops. So the reaction rate of forward reaction is drop. But the reaction rate of the backwards reaction, reverse reaction, increase. Why? Because we get more and more what? Product, because you're producing more and more. If you produce more and more, then reverse reaction will increase. Eventually, they will become equal at this point. At that point, we call it chemical equilibrium. At chemical equilibrium, what's equal? Again, the reaction rate of the forward and the reverse is equal. The rate is equal. But the concentration of the back and forth of these two versus that one is not equal. You can think about city A. Let's talk about two cities, A city, B city. A city has 80 cars, let's say. Two city has 20 cars. Let's say A city and B city reached equilibrium, means how many cars going to be and the same amount of cars going to A. But the reaction is still happening. Means the total number of cars don't change. 80 is 80, 20 is 20. Why? Because 5 cars goes to B and then 5 cars go back to A. But the 80 and 20 doesn't have to be equal. Equal means what? Equal means their rates are equal. Means the total number of cars don't change, but doesn't mean they're equal. The same, you can see that here. After reached equilibrium, H2 and I2, they don't change anymore. HI doesn't change anymore. Why? Because back and forth is equal now. But H2 and I2 versus HI, the concentration don't have to be the same. Again, guys, you can always use this example. Think about two cities reached equilibrium. First city has 80 cars, the second city has 20 cars. If they reach the equilibrium, how many cars going to B city? How many cars will go back to A city? The same. So 80 and 20 never change anymore, but 80 and 20 doesn't have to be equal. Does it make sense, guys?
Yes.
So last summary about the chemical equilibrium is when a system reaches chemical equilibrium, the forward reaction rate and the reverse reaction rate, what? Equal. Guys, make notes, please. What is chemical equilibrium? Forward reaction rate equals to reverse reaction rate. What about concentration? The concentration of the reactants and the products don't change anymore. 80 cars is 80, 20 cars is 80. They don't change their money, but they're still exchanging back and forth because equilibrium is not stopping. They're just equal. So 2 facts, guys. First fact, please, when you watch the video, you can watch multiple times. I'm sorry, I'm keep talking about. When a system reaches equilibrium, forward reaction rate equals to reverse reaction rate. At that point, the reactants concentration and the product concentration are not equal. They just don't change anymore. Does it make sense, guys?
Yes.
Okay, you can see this flat. Flat means what? They don't change anymore, but they're not equal. What's equal? Here is equal. Rate is equal. Okay, that's everything about a chemical equilibrium. Now, let's take a look. How do we quantify a chemical equilibrium? We quantify the chemical equilibrium use a term called equilibrium constant, K, capital K. And we put a subscript EQ stands for equilibrium. What is equilibrium constant? Equilibrium constant equals to the product concentration. Sorry, I'm missing some brackets here. Your notes may have it. The product concentration powered by the coefficient of it divided by the reactants concentration powered by their coefficient. You can see that here. For example, bracket C means the concentration of C. C is one of the product. Y, the superscript Y exponent is what? Is the coefficient of Y. What is coefficient, guys? When we balance the equation, the numbers in front of it is called coefficient. Don't forget. And that's called equilibrium constant. No math required here, but guys, I will test you in your quiz and exam of writing a chemical equilibrium constant. You only need to write it down or called expression, how to express it. You don't have to do any math. Chem 111, 112 would be a lot of math on it, but for you guys, no math. But you have to show me the expression of it. What is the expression? K equals to the product over reactant concentration. The brackets means concentration, molarity, powered by their coefficients, respectively. Okay, for example, guys, take a look. This is an equilibrium. K of it equals to what? Take a look. CO concentration times hydrogen concentration powered by 2. Why 2 here, guys? Why 2 here?
There's a 2 in front of H2.
Because the coefficient of H2 is what? It's 2. And divided by the reactant concentration. Why there's no exponent? Because the coefficient is 1. That's why there's no exponent. Does it make sense, guys? Check back and forth. Again, I will test you both in your test and final exam. Don't tell me I didn't tell you. Okay, here are some few facts. The first few we talked already. Square brackets refer to concentration. Product is called the numerator, means on top. Good number. I have a hard time distinguishing the numerator and denominator. Okay, I only on which one top, one and bottom. Sorry. Product top, numerator they're called. Reactant bottom, called denominator. The coefficient in the balanced equation determines what? The powers, the exponent. And KEQ means equilibrium constant. These are the ones we talked already. Now, two important facts we haven't talked about, but we're going to test you as well. Only when the reactant is a gas or when the reactants are in a solution will need to be included in the equilibrium constant. Only when reactants are gas or when reactant is a solution, they will be included in the equilibrium constant. Why? Because gas and solution have a concentration. That's why we use, because remember the brackets means what? Concentration. Whatever here is a concentration. Only gas and solution have a concentration. That means if you have a pure solid or pure liquid, pure solid, you do not include that in the equilibrium constant. You do not include that in the equilibrium constant. Pure liquid, such as water, pure gas, pure solid, you do not include that into equilibrium constant. Why is that? When something is pure, liquid or solid, doesn't matter. The concentration is what? Anybody? Can anybody tell me when something's pure, what's the concentration of it?
I don't know what it be. It would be either 0 or 100%.
Which one?
I don't know.
It's 100%. Why? It's pure, right? What's percent means? Parts overall. If something is pure just by itself, means what? Parts is himself, all is itself. What's the concentration? 1. 100% is 1. If it is 1, we don't care. I mean, it doesn't, when in the math wise, dividing 1 or times 1, there's nothing changed. So that's why, again, pure liquid, pure solid, do not include in the equilibrium constant. I will test you guys. Okay, how would you tell it is pure liquid or solid? Very easy. Take a look. What does the parenthesis mean, guys? What does the letter in the parenthesis mean? We talked about it earlier. What does it mean?
G means gas.
G means gas means what? This is the physical state of the reactants or products. You will be told if it is solid, you will see an S over there. If it's liquid, you'll see an L over there. It's super easy. Only is you need to memorize that fact. Again, these are the tricky part, how the tests are designed. So you answer, if one question can test you both. Can you write the equilibrium constant? Number 2, did you understand solid and liquid, their concentration is 0, is 1? See? Next, let's take a look. What does an equilibrium constant tell you? Why we use that? Okay, why we use that? Let's take a look this reaction. Okay, one more time. A, B, C, D. Okay, A, B, C, D. C, D. Let's say the coefficient is 1. Let's to simplify us. So K equals to what? C times D concentration divided by what? A concentration divided by what? B concentration. Again, I am assuming the coefficients are all not 1. So we simplify our math. Take a look, K. K equals to product over reactant. So that means if I have a big K, if K is large, what does it tell you guys? Look at this. This is equilibrium constant. If K is large means what?
There's a lot of product.
A lot of C and D and what? Tiny amount of A and B. Is that right, guys? Math, think about math. If something is big by dividing, the ratio is big means what? The numerator is big, the denominator is small. Top is big, that's how you get a big number, K. So equilibrium constant tells us when we have an equilibrium, which part, which way, left or right, is favored. What is the relative location of the equilibrium? If we have a huge K, very big K, in this case, they give an example. What is a very big? It's 10 to the 30th. Okay, 10 to the 30th. That means we essentially have all the products because it's too big. C and D is almost everything. You don't have any A and B because the K is so big. So we essentially have all the products. Reaction favors what? Favors C and D. In that case, that's why sometimes you guys, all the reaction we learned before, we never use the double arrow. We use what? Single arrow. It doesn't mean the reaction is not reversible. It means what? The reaction favors the product too much. We assume nothing is left for A and B. Does it make sense, guys? Now you know all reactions actually reversible. Why sometimes we only use one way? Because those reaction K is huge. Huge means you rarely have any A and B left. Everything goes to C and D. Does it make sense, guys? Everyone?
I think so.
Now, if we have a very small K, think about, means what? Extremely small K means what? C and D is small. A and B what? Is huge. Is that right, guys? Does it make sense mathematically? If I have a small K, like 10 to the minus 30th, think about what 10 to the minus 1 over the 30 is. 1 over the 30 means what? I have 1 of C and D and 10 to the 30th of A and B. Means what? Means the reaction essentially doesn't even occur. Almost everything is A and B. You only have 1 C and D. Does it make sense, guys? Think about it.
So what would have happened to C and D?
Almost nothing. The reaction doesn't even happen. You have A and B as product, as reactants. The reaction doesn't even go to the right. Why? Because K is small. Does it make sense?
Now I'm still having a little trouble understanding this, I think.
First, for the big one, what 10 to the 30th means what? Let's not use 10 to, let's use 10 to the a million. If K, think about it, guys. If K is a million, means what? Means a million to what? To 1. Is that right, guys? Do you agree with me, guys, everyone?
Yes.
If K is a million, with a million to 1 means what? Means C and D is a million. A and B is what? Is 1. Is that right?
Yes.
Is that right? So it means what? Means you have a million products, you have 1 reactant. Means what? Reaction favors where? To the product. We assume the reaction is 100% already. I mean, out of a million, you only have 1 reactant left. Means what? The reaction is clean. You don't have any you almost have no A and B left. Does it make sense now? Does it make sense now, guys? We have a reaction now, A and B to C and D. If K is huge, this is not even huge. A million is not a huge, but let's say a million, because a number you can visually understand. So if I have K equals to a million, means a million to 1. Million to 1 means what?
So that means
million.
that
Yes.
from the reaction, there are all products and no more reactants.
Almost no, because 1
got it.
assuming is like a, yes, almost product. Means what? Reaction favors to the right, favors C and D. In
Okay,
that
that
case,
makes
I can
sense.
use a single arrow now. Why? Because I assume the reaction go all the way to what? To C and D. Does it make sense?
Yes.
Now, let's say if K is not a million, if K is 10 to the negative 6, what does it mean? Means K equals to 1 over a million. Means what? Now C and D is 1. A and B is what? A million. What does it tell you? Tell you the reaction almost what? Didn't go, because a million is still the reactant. You only got one product. We even can say the reaction didn't happen. Does it make sense?
Yes, thank you for explaining that.
Okay, again, this is what K is useful. If you have a huge K, means what? Reaction favor to the right. If you have a tiny, small K, reaction favor to the left. We assume the reaction, if the K is too small, like this, here, 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 we even assume the reaction doesn't happen. But again, in nature, there's no absolute thing. We all call everything is under equilibrium. It just favors which side. That's why all the reaction you see, okay, I'm using a single arrow. It doesn't mean it's not reversible. It's still reversible, but it favors to the right too much. Does it make sense, guys?
Yes.
Okay, again, there's no math here. Only thing you need is understand, be able to explain. Okay, you will have a question. I remember that in the quiz. I give you a equilibrium constant K. I ask you, hey, can you choose which one do you think that reaction is? If K is big, again, means what? You have almost all products, only what? Tiny reactants. If K is small, means you have almost reactants, tiny product. If K is middle, for example, you got both. Okay, for example, if K equals to 1, guys, means what? Means 1 to 1 means what? You get half reactants, half products. The reaction is like that. So the K is used for us again to determine the position of an equilibrium. Okay? Sometimes, if we know the position of an equilibrium, for example, if I know the, hey, this reaction, if I know the reaction favors to the left, I can put the arrow to the left longer, the arrow for the right shorter. This one, I can tell people, hey, the reaction favors to the left. And by the way, guys, this is the reaction. You guys put carbon dioxide or you breathe carbon dioxide in water. This is what happens. Carbon dioxide will react with water to produce H2CO3. That's called carbonic acid. But the reaction favors to the left. That means you can't get too much of that. Okay, that's the same reaction happening in your Coke. You know, Diet Coke or whatever Coke. The gas is what? Carbon dioxide. When you open it, the H2CO3 decompose a lot. Okay, why? Because pressure is released. Okay, pressure is released. The reaction favors to carbon dioxide. Okay, carbonic acid is very unstable. You can see the arrow favors to the left. Okay, here are some practice for you to write the equilibrium constant. The one, I don't do it here, but again, guys, two things. One thing is you understand how to write it. Products over reactants powered by their coefficient. And number two, remember this fact. If you have a pure solid and pure liquid, do not include that in an equilibrium constant. For example, here, take a look at this case. This is a solid. That's a solid. Means what? Practice. Okay. This one I'll leave it for a practice. I'll practice this one with you together. Because we know equilibrium constant is product over reactant powered by their coefficient. So if I give you a K expression, you can actually write the reactions based on the K. What does it mean? Things on top are what, guys?
To the
top are what? A product. So see, I put this on in product. Things on bottom are what? Reactants. So I put it on the left side of the arrow. And their exponents are what? coefficient. That's why, see, 4 is for NO, 6 is for H2O, 4 is for ammonia, 5 is for oxygen. So here, this example, I want to show you, if I give you, or if you know the expression of the equilibrium constant, you can write the reaction, like doing reversely. In the previous example, I ask you, hey, I give you the reaction. Can you write the equilibrium constant? Yes, product over reactants. But you can also do it backwards. Okay, this is how we do it backwards. Something on top are what? Products. Of course, you need to get rid of the bracket. Bracket means concentration. Something at bottom are what? Reactants. And the exponents, the powers are their what? Respective coefficients. Does it make sense, guys, everyone?
Yes, I do have a question about the previous slide. What you were saying about the solutions.
Yes, this one?
Yes.
Yes,
You were
go ahead.
saying if they are gases or if they are in a pure solution, don't include them in the expression?
Not pure solution.
Not pure.
Gas equilibrium constant only includes gas and solution reactants or product. Don't include pure solid or liquid. Solution is not a pure liquid. Solution is a mixture. Does it make sense?
So in the middle one, you have a solid as a reactant and a solid in the product.
Yes. So what? We don't want, we include or not?
From what you just said, you wouldn't include.
Correct. You don't. So the K equals to what? CO2. That's it. That's the K.
Okay.
That's the product. CO2 is the product, so on top. The bottom one is 1 because there's nothing in there. Does it make sense?
Yes, thank you.
Okay, again, pure solid, pure liquid, we do not include in the equilibrium constant. We include gas and solution. Gas, you will see G. Solution, you will see AQ. Okay, AQ means aqueous solution. Liquid and solid, you do not include. Okay, for example, that's the K for the second one. Okay, that's the K for the second one. All right. Let's move on to the last part of this topic. Is what if I did something to change the already established equilibrium? Or in this word, if I apply a stress to a already established equilibrium, what will the equilibrium do to adjust itself? Or what direction will the equilibrium move to adjust itself? And this topic, or this direction, determination, is called this principle. I don't know how to pronounce it. You guys can find Google and tell me tomorrow. Le Chatelier principle. This principle basically tells us if I disturb an equilibrium already established, what will the equilibrium respond? Okay, what happened for the equilibrium? And this principle can be summarized in a few words or half a sentence. The equilibrium will respond in the direction that, take a look at the one you read, reduce the stress. Reduce the stress. So 3 words, I would say. Reduce the stress. reduce the stress. Guys, keep that all in mind. We'll have a few examples to show you what is reduce the stress mean. Now, before we took out the real reaction, let's take a this one, this water connection device. It's not a chemical equilibrium, but it kind of show you this principle. Just like the car thing, very similar to the car. There's like two cities with some city has bigger, more water, some cities less water. They're connected. Let's say now the water level is the same. So we call, hey, A and B, two water reservoir reached equilibrium. You guys agree?
Yes.
Water is still moving. Okay, don't water molecule moving around. So we call this is equilibrium. Again, it's not a chemical equilibrium. Let's say, guys, if I add water to the left, let's say this is the amount of water I add. Here, add. Tell me, what do you think will happen? I mean, you don't even need the principle. You know what happened. What will happen, guys?
Water in the bigger one will go down and it will level out in the smaller one.
Good. The water will move to where? To the right. Is that right, guys? Is that right, everyone?
Yes.
Yes.
Now, water will move to the right. That is the response to the disturbance. The disturbance is what? I add water to the left. And then the water will move to the right. That's what happens for the equilibrium. Will respond to my disturbance. Move to the right. But why we call this reduce the stress? Think about it. When water moves to the right, the water on the left will what? If I add this much, the water will actually what? Drop. Is that right?
Yes.
Did it reduce the stress?
Yes.
Did it reduce the stress? Yes, it did. I add this much, and water will go to the right, so the water will decrease. But in the end, when the system goes to flat again, the water level will be like what? Like this. Do you agree?
Yes.
Do you guys agree? Still, the new water level will be what? Higher than the original. Do you agree?
Yes.
Why? Because I added water. That is what these three words mean. Reduce the stress. You cannot take away the stress. The stress is there already. Why? Because you added water. The new water level will still be higher, but the system moved to the right. So the stress is reduced. Guys, put this word in, three words in your mind for a million times. You will answer the questions based on these three words. And you have a lot of questions in this part. And they're very easy question. Don't make mistakes. One question, multiple choice, 4 points for example. They're easy. If I tell you, you will say, oh, I know it. But please be careful. Always ask yourself, did it reduce the stress? Reduce the stress means water moved to the right. Reduce means it does not take away the stress. The stress is there, means the final water level here is still higher than the original. Why? Because you added stuff. So if you understand this, let's take a look at some real example. Here I have a chemical equilibrium. If I add product on the left, this case, if I add product, the equilibrium will try to what? Reduce the stress. How to reduce? Move to the left to get rid of some of the product. Some, I said, get rid of some, not get rid of all. Why? Because there's not taking away the stress, reduce the stress. So when you add product, the equilibrium will move to the left. We call it shifts left. When you add reactants, just like they add water to the big tank, the equilibrium will shift to the right. Does it make sense, guys?
Yes.
If you remove something, the opposite. If you remove the product, for example, reaction shift to the right. If you remove reactants, reaction shift to the left. Again, we're talking about add, remove, opposite. Here, another example. This is the equilibrium reached already. I have 5 NO, 5 N2, 7 H2, and 5 NH3. Let's say, assume that these are number like fake numbers. But at a certain time point, I disturb the equilibrium by adding 3 more hydrogen. Hydrogen is a what, guys? Take a look at the equilibrium. Hydrogen is a what?
The reactant.
The reactant. So what will happen? If I add hydrogen, the equilibrium will shift to where?
Product.
Shift to the right. Because I want to use some of the reactants. Because I added some reactant. I want to reduce the stress. What's the stress? Adding reactant is the stress. How do I reduce it? Consume it. How do I consume it? Move to the right. If I move to the right, take a look. These are the new numbers. This example is perfect for you to understand this principle. If I move to the right, NH3 is actually what? Going up. Hydrogen go up, even though it's reduced from the 10. You have 7, you added 3. The reaction, the equilibrium shifts to the right, consumed some, still you end up with 8.3, which is higher than what? Higher than that 7. Why? Because we're reducing the stress. We cannot take away stress because you still add H2. Now, when the reaction go the right, the equilibrium shift to the right, nitrogen is actually what? Decreasing. Why? Because equilibrium shift to the right. Some nitrogen is used. You didn't add nitrogen, you add hydrogen. Does it make sense, guys? Take a look at the numbers. It will help you to understand, reduce the stress. Does it make sense?
Yes.
Okay, guys, add hydrogen, adding the reactant, reaction shifts to the right, you get more product. Nitrogen will decrease because you need nitrogen to shift to the right. Hydrogen will still end up higher than original because you added 3, but it will decrease from that total, but still higher than the 7. So this is the final number for those 3. Again, they're fake number, but kind of tell you, hey, this is what we're looking at for reducing the stress. Stress is more hydrogen. System want to get rid of some. How to get rid of some? Shift to the right. So always ask you this way, guys. Okay. I'll do one practice with you and left the second one with you. Then we move on to the next disturbance. Here I have an equilibrium. If I add water to the flask, water is a gas here. Take a look. Water is G. How does the concentration of each chemical compare to the original after the equilibrium is re-established? First, if I add water, the equilibrium shifts to where?
To the right.
To the right. If the equilibrium shifts to the right, these two concentration will what, guys?
Higher.
Higher, increase. Okay, increase. Because I shift to that, I get more products. If I shift to the right, this concentration will what?
Decrease.
Decrease. Okay, decrease. Why? Because I used them to shift to the right. I didn't add CO, I add water. And reaction shift to the right, CO will be consumed. If CO is consumed, it will decrease. What about the concentration of H2O? Guys, what about the concentration of H2O? Hello?
In the previous one, it increased.
It still increased. Okay, still increase. Remember, you added. The system can only reduce the stress, cannot get rid of the stress. Okay, H2O is still increased. They're actually compared to the original. Take a look at the word. Compared to the original. Compared to the original, water is still increased. So here's the change. H2 and CO2 are products. Their concentration increase. Water, because you added, concentration also increase. CO, because the equilibrium shift to the right, you consumed it, the concentration will decrease. Okay, will decrease. Here, this one you practice using the same logic. Next, okay, next. If I don't add or remove things, if I change temperature, what will happen for the equilibrium? In order to understand the temperature effect, first, I need to show you how do we write an endothermic reaction or exothermic reaction in an equation? Or how do we show people, hey, my reaction is endothermic or exothermic using an equation? In endothermic equation, we know is what? Absorbing heat, taking in heat. So I can add heat as a reactant because I take in heat. So you can see that for endothermic reaction, if I want to show people, hey, this reaction is endothermic, I can add heat as a reactant. I mean, not real reactant, it's heat. But again, heat will be placed on the left side because absorbing heat. Exothermic means releasing heat. So I put heat as a product because released heat. Does it make sense, guys?
Yes.
We're talking about temperature. We have to discriminate endo and exothermic. Now, if you understand that, it will be very easy to understand the temperature effect. For endothermic reaction, increased temperature means add heat. Add heat. Heat is a reactant. Take a look for endothermic. Reaction shifts to the right. Decreased temperature means remove heat. Remove heat means reaction shift to the left. And for exothermic, it's reverse. I'll give you a couple minutes to understand this. If you have any questions, please ask me now. The effect of temperature depends on the type of reaction, whether it's endo or exothermic. Endo, we put heat on the left because absorbing. Exo, I put heat on the right because it's releasing. Increased T means add heat. Depends on which side you add it. For endo, you add on the left, on the right, other side, right. Okay, I put it here again, guys. Take a look. Please let me know if you have any questions. No, guys, are we good?
I think I'm good.
All right, take a look at the experiment. Okay, it's a very nice experiment we should have done in the lab, but we don't because cobalt. Cobalt is a toxic heavy metal, so they can't ship it to you with your kit. Normally, we have this lab in our chemical lab. Okay, you can see that cobalt chloride with chlorine react with water, so water can be conjugated with cobalt. So we have two species in the equilibrium. This one is blue and this one is pink. The reaction is what? Guys, can you tell me, based on the equation, can you tell me whether it's endo or exothermic?
It looks exothermic.
Exothermic, very good. Now, if I remove heat by placing this thing in ice means what? Decreased temperature. Decreased temperature means remove heat. If I remove heat, what happens? Reaction shift to the right. The equilibrium shift to the right. Shift to the right, the thing will become what? Pink. Why? Because this thing is pink. That's what it has to see here on the picture. Do you guys see that? Put in the ice, remove heat because heat is a product. If you remove product, the equilibrium will shift to the right to give you more heat. Again, think about reduce the stress. What's the stress? You take heat away. If you take heat away, the system want to do something to what? To get more heat, reduce the stress. How do we get more heat? To the right, because right will produce heat. Does it make sense, guys? For all these? Okay, and of course, the thing will show as pink. That's why we do experiment, hey, to prove that, hey, put in the heat, you will see pink. Then this gives us the Lesch-Delier's principle, right? Next is changing the pressure. Changing pressure will only affect when gases are involved. If you have a solution equation, no gas involved, pressure will not have any zero effect on it. Changing pressure only affect gas reactions when gas are involved. And pressure change has an effect on the volume. Okay, pressure change is brought about through volume change. Meaning, if you increase pressure, Boyle's law, increase pressure means volume will decrease. When volume decrease, the equilibrium will shift to the direction with fewer moles of gas. When you decrease volume, the equilibrium will shift to the direction with fewer moles of gas. Take a look, this reaction. On the left, there are 4 moles. On the right, there's 2 moles because the coefficient left is 1 plus 3, the right is 2. So if you increase the pressure, decrease the volume, the equilibrium will shift to the one with fewer gases, to the right in this case. Why? Because to the right has fewer gases. To reduce the stress. The stress is volume is too small. I want to reduce that. I want to get less gas. The same idea, if I decrease the pressure, increase the volume, the system want to produce more gas, then the equilibrium will shift to the direction with more moles of gas to the left in this case. Does it make sense, guys?
Yes.
Okay, and finally, 2 things. Don't change the equilibrium position. One is inert gas. No matter how much you add, they don't change the equilibrium position. They have no effect. What are inert gas? Noble gases, such as helium, argon, neon, etc. That's one thing. Remember, adding noble gases, inert gases, they don't change equilibrium position because they don't change the pressure, the partial pressure. Another one is adding catalyst. What is catalyst? Increase the reaction rate. But catalyst increase the reaction rate of forward and reverse equally. So adding catalyst simply means the equilibrium are faster, but they're still the same. So it does not change the position of an equilibrium either. 2 things don't change, inert gas or catalyst. Again, we know catalyst is something increase the reaction rate, but it increased both the forward pathway and reverse pathway equally. So in the end, they're still equal. It's just both are faster. But equilibrium position do not change. Okay, do not change. Okay, that's all for this chapter. Let's practice few. We have a few minutes. Okay, a few minutes. I'll ask some of you to answer this question. What is the effect of adding CO2 to the equilibrium? Becca, sorry. Adding CO2 to the equilibrium, what will happen?
Just a second.
Caroline, what is the effect of adding CaCO3? They're separate questions. Don't affect which one everyone gives the answer first. It doesn't matter because they're not separate questions. Caroline, what is the effect? Oh, sorry. Either one of you, please let me know when you're ready. We have, I'll give 1 more minute.
There will be it'll be an exothermic reaction.
No, this one has nothing to do with exo or endo.
I'm not sure.
Adding CO2. CO2 is a what? Is a product. Adding product will shift the equilibrium to where? To the left. Why? Because adding product, the equilibrium wants to reduce the stress. What's the stress? Too much CO2. How to get rid of it? Shift to the left. Use it. So adding CO2, the equilibrium shifts to the left. Caroline, what is the effect of adding CaCO3?
The equilibrium will shift to the right.
I saw where you're coming from, but unfortunately that's not correct. The reason is CaCO3 is not a gas or solution. It is a what? It is a solid. The solid does not affect the equilibrium. So adding additional CaCO3, it actually has no effect on the equilibrium. Why? Because no matter how much you add, the concentration of it is always 100% because it's a pure solid. Does it make sense?
Yes.
All right, 1 more practice, I promise. I'll let you guys go. What is the effect of a decreasing the volume on the reaction mixture? Olivia? Decreasing the volume on the equilibrium.
Give me 1 second.
Okay.
I'm not really sure.
Decreasing the volume, what's the stress? Too crowded. If it is too crowded, the system want to what? Make it less crowded. How do we make it less crowded? Less gas. How do we make less gas? Shift to the left, because you don't have any gas on the left. You have 3 gas on the right. Do you guys see that, everyone?
Yes.
So decreasing the volume will shift the equilibrium to the left. Why? Because the stress is too crowded. The system want to reduce the stress by producing less gas. Shift to the left. Okay.
So
and of course,
the reaction
yes.
mixture, does that refer to the left side or the right side? I'm confused.
The whole thing. This equilibrium, you have both things. You're in the same flask. You have both of them, because equilibrium means what? You have some reactants to the product, some products to the reactant. Everything is in the same in there. You're not adding on the left or adding on the right. You're adding something to the mixture. This is an equilibrium. Does it make sense?
Yes, thank you.
For example, A, B, and C and D. You have A, B, and C and D all together in the flask. Just some ways more, some ways less, but you have all together. Questions, guys? All right, that is all for this chapter. Please use the rest of these one we haven't done or the one we have done to practice and make sure you understand these shifting of equilibriums and this Leschender's principle. Again, like I said, you will have many questions in the final and in your next quiz. Okay, I'll see you guys next Tuesday for chapter 10. Okay, we'll start chapter 10 and we'll finish chapter 10 as much. Chapter 10 may takes 3 lectures, and your quiz on chapter 9 will be on Wednesday. We'll do a review and a few practice, hopefully, for the quiz. And have a good weekend, guys.
I do have a question. Would you
Yes.
announce next week's lab?
I'm sorry, I do what?